Hi everyone. In the previous session, we have discussed what is quantization noise with respect to uniform quantization. Now, let us derive what is signal to noise ratio for uniform quantizer. So, according to definition of quantization noise, quantization noise can be defined or denoted as epsilon, which is equals to the output minus input. Output is the quantized output, the quantized value minus the actual input. If you take the difference, if both are same, if input is exactly mapped to the quantization output, then error will be 0. But practically there may be some difference between the actual signal G of NTS and the quantized value GQ of NDS. In that case, we have error called epsilon. So, as I said, GQ of NTS is the quantized output, GQ of NTS is the quantized output, and G of NTS is the actual input signal that we are feeding for the quantizer. So, the difference between them will give you what is the quantization error. Now, let us take a range. Suppose if this is your signal, so from max to min, this complete range, okay. So, I will represent it as, plus G max and this is minus G max. Therefore, the range is from minus G max to plus G max. This is total range. So, from minus G max to plus G max. So, in that scenario, the total amplitude is, it is difference between that G max minus of minus G max. So, it is totally 2 G max is the total range of the input signal, the total amplitude range of the input signal. So, now let me code this with a range divided into Q levels. Suppose this can be divided into level 1, 2, 3 like this. So, levels we are dividing the input signal into, let me say, Q number of levels. Q number of levels of the quantizer where the step size being delta. So, step size means, as I said in the previous video, it is the difference between the previous level and the next level. So, in that case, what is the step size? That is, what is the difference between one step to the other step? Suppose if I take this is the difference between one step to the other step. So, that can be, it is maximum amplitude divided by number of levels will give you what is each step size. So, the maximum range is 2 G max as we seen in equation 2 divided by number of levels is Q, so that you will get each step size, that is called delta. Okay, so we represent step size as delta. Call it as equation 3. So, if this signal, the input signal G of t is normalized. So, normalized means I am selecting the G max value as 1. Similarly, minus G max becomes minus 1. So, the amplitude is from minus 1 to plus 1. Okay, totally. So, G max is 1 and minus G max is 1. Therefore, now delta can be written as. So, since G max is 1 in the equation 3, this G max is 1 for normalized value, then delta becomes 2 divided by Q. So, this is the step size for uniform quantizer if the amplitude is divided into Q different levels. So, let us assume the quantization error will be uniformly distributed, it is a random variable. Then, so we know that for uniform quantizer, so again we have derived this in the previous video, I will share the link in the description, you can go through. So, maximum error that you can get through is delta by 2. So, that is magnitude of delta by 2, either it is minus delta by 2 or plus delta by 2, within that range itself. So, your error will lie. So, therefore, epsilon max is magnitude of delta by 2, call it as equation 4. Let us draw the probability density function, so which is defined as, so as we know, so we are plotting the error with respect to probability density function. So, PDF Now, so we know that epsilon will be there only between minus delta by 2 to plus delta by 2 from equation 4. So, you can observe that. So, epsilon max is between minus delta by 2 plus delta by 2, and since it is uniformly distributed, so I will take this rectangular function. Okay. Now, so since I am representing a probability density function, whenever epsilon is less than minus delta by 2, you can observe that it is 0. So, that is what indicated here. Whenever it is less than delta by 2, minus delta by 2, so the function is 0. Similarly, when it is more than delta by 2 plus delta by 2, when it is more than delta by 2 also, it is 0. Correct? So, this one, whenever it is epsilon more than delta by 2, again it is 0. So, now between minus delta by 2 to plus delta by 2, we have some error. So, that function I need to write, and I want to find out what is the magnitude of that. So, which is given by 1 divided by, so suppose if I say this is the limit b and this is a, then 1 divided by b minus a. So, 1 divided by what is b? It is delta by 2 minus a is minus delta by 2. Minus of minus becomes plus, therefore, delta by 2. So, 2 if you take it as a LCM and bring it to the numerator, it becomes 2 by 2 delta. So, it becomes 2 divided by delta plus delta is 2 delta, 2 to get cancels. So, you will remain with 1 by delta. What is this function? So, probability density function. So, which I have written here, when your epsilon is between minus delta by 2 to plus delta by 2, your function is 1 divided by delta, otherwise it is 0. Okay. So, this is your probability density function. So, if I want to calculate what is the mean square value of random variable epsilon, so mean square value we know the formula. So, if any function epsilon, if you want to find the mean square or estimation of epsilon, so we call it as E of epsilon square, mean square value. So, this is the formula for mean square value. How you calculate? Integral from minus infinity to plus infinity, whichever the function you are taking, that is epsilon square, into probability density function of that. Okay. Now, let us substitute what is probability density function, this value f of epsilon. Okay. So, if I substitute from the previous equation, so it was 1 by delta, right? It was 1 by delta between the limits minus delta by 2 to plus delta by 2, otherwise it was 0. So, I have not considered 0, because if you consider also, so the output will be 0. So, only between the limits minus delta by 2 to plus delta by 2, I had probability density function which is 1 by delta. So, if I substitute that here, so this becomes epsilon square, I am writing as it is. Okay. Then in place of probability density function, I am writing 1 by delta into d epsilon. See, if I simplify that, so 1 by delta is constant because we are integrating with respect to epsilon. So, I will bring 1 by delta outside. So, what is the integration of epsilon square with respect to epsilon is epsilon cube by 3. So, epsilon square integration is epsilon cube by 3 with the limits minus delta by 2 to plus delta by 2. Now, if I simplify again, so this is constant, I will write it as it is 1 by delta. Now, you apply the limits, upper limit is delta by 2. So, wherever you have epsilon, you put delta by 2, therefore, it becomes delta by 2 whole cube whole divided by 3 is there in the formula, plus again lower limit, okay, upper limit minus of lower limit is minus delta by 2. So, minus delta by 2 whole cube divided by 3 is there in the formula. So, we have written. So, now, so if you see that 3 is common in both the terms. So, you can take it as 1 by 3 delta outside, you will remain with delta by 2 whole cube, which means that delta cube by 8. Again here delta by 2 whole cube, which means that delta cube by 8. So now, so it becomes again 8 common. So if you bring it outside, so if you bring it common, so it becomes 24 delta, correct? So 8 3s are 24 delta into 2 times of delta cube, correct? So 2 1s are 2 12s are 24 and 1 delta you have and cube here, therefore it becomes square. So you get this equation as del square by 12. 1 delta get cancels, you will remain with del square by 12. So this is the estimated value or the mean square value of the noise epsilon, so which is given by equation 7. Once we know the estimated value, so we will find out what is the power. So we know that according to Ohm's law, P is equals to V square by R. So whether it is a noise or a signal, P is equals to V square by R. So noise power is equals to V square by R. So where V square noise means it is a mean square value, that what we already calculated in equation 7. Okay. So therefore the normalized power, okay, so V square noise we already found out from equation 7, that is a mean square value. Okay. So next is noise power. So what is noise power? So it is V square, that is del square by 12, that is what we calculated from equation 7, divided by R. So I assume it is a normalized power, therefore R is equals to 1. R is equals to 1 for normalized power. So what is my intention? My intention was to find out signal to noise ratio for a uniform quantizer. So we know that from the definition of signal to noise ratio, it is signal power by noise power. It is signal power by noise power. So it is signal power by noise power. So now we already calculated what is noise power from this equation, correct? It is just del square by 12, that is what we have substituted here. So normalized signal power we don't know, because we have not assumed what is the nature of the input signal. I will assume the normalized signal power being P. Before that, let us assume there are V number of bits in each level. Then I can write, so Q is equals to 2 to the power V. Q means number of quantization levels and V is the number of bits used for each quantization. So substituting equation 10 in equation 3, what was equation 3 is delta. It was 2 G max by Q. So in place of Q, I will write it as 2 to the power V. Suppose if you are using only 2 bits, then it becomes 2 to the power 2. Okay, if you are using 3 bits, then it becomes 2 to the power 3. Okay, so that determines the step size delta. Therefore, substituting equation 11, so that is the value of delta, substituting equation 11, the value of delta, so in signal to noise ratio. Okay, so when you substitute in signal to noise ratio, letting the normalized signal power P, that is, since we don't know what is the nature of the signal, I will assume the normalized signal power is P. If I substitute P here and rewrite equation 9, we get signal to noise ratio is equals to, how you get 12P? If you go to previous slide, so you have 12 in the denominator, so delta square by 12. So this will come to the numerator, so it becomes 12 into P. So if you take 12 into P, and so next you have, how do you get this? Delta square. So we know what is delta, right? So from equation 11 we know what is delta. It is 2 G max by 2 to the power 2V, 2 to the power V. Now you have to square it, because we have delta square in the equation. It becomes 2 square, 4 G square max divided by 2 to the power 2V. So that is what it is written. So 2 square is 4 G square, and 2 to the power V whole square is 2 to the power 2V. Okay. So now if you simplify this, 4 1s are 4 3s are, you will get 3P. So you will get G square max. So again this will come to the numerator again, that is 2 to the power 2. This is signal to noise ratio for a uniform quantizer assuming the normalized P, assuming the normalized power, input signal power P. So again simplifying this, so we will get it as 3P divided by G square max into 2 to the power 2V. So this is actually comes to the numerator 2 to the power 2V. Same equation is written here. So let me call this as equation 12. Now what is equation 12? It relates signal to noise ratio and number of bits V. So it gives the relation between the number of bits V and signal to noise ratio. So if the destination signal power P is normalized, okay, that is P I will assume 1 or less than or equal to 1, then the above equation becomes signal to noise ratio. So I am assuming P as 1 or less than 1, therefore it is less than or equal to 3 into it becomes just 2 to the power 2B, because for normalized power, so P is less than or equal to 1 and also G max is equals to 1, we know, we have assumed. Therefore, so you will get equation 3. This is a signal to noise ratio of a uniform quantizer. Now let us represent this in decibels. So if you represent this in decibels, how we will represent it is 10 log of the signal to noise ratio. If you take 10 log of the value, you will get it in decibel. Okay. If you get 10 log of signal to noise ratio of equation 13, okay, so you will get it in decibels. So therefore, so it is less than or equal to 10 log of, so we know what is the expression for signal to noise ratio, that is 3 into 2 to the power 2V, that is what substituted here. So it is 10 log of 3 into 2 to the power 2V. Now, so if I calculate the value, so 10 into log of 3, if you calculate, you will get it as 4, and so 10 into log of 2 to the power 2V, it becomes 20 log 2, so which is equals to 6V. Okay. So this is how you can represent in decibels. See, this question, so is when signal to noise ratio you are finding out of a uniform quantizer, assuming the signal nature is not known. So if the signal is known, to you, so then what you can do it is, so instead of assuming P is 1, okay, so I will take the actual value of P, okay, so I will take the, so you have to do it till this point. If the signal to noise, if the input signal is assumed as a sinusoid, let me assume it is a sinusoid, then you have to continue till this point, whatever I have done till now. Then instead of doing this, okay, so we will do the different steps. Okay, same question I am asking, derive an expression for signal to noise ratio of PCM system. Here you can observe, assume that input to PCM system is sinusoidal. So in the previous slide, so I have not assumed it is sinusoidal, it is general signal. Okay. So now let us again, I will continue with equation 12, which is I have marked. So what was the equation here? So this was the equation, if you remember, signal to noise ratio. This was the equation you got, 3P divided by G square max into 2 to the power 2B. Okay. Now P means the signal power we need to calculate. Because I assumed the sinusoidal wave, then the amplitude of the sinusoidal is AM, amplitude of the message signal is AM. So we know that power is V square by R. V square means it is root mean square value. Therefore, I will take AM by root 2 whole square. It is a root mean square value, that is V square we got. So power is equals to V square by R. So assuming R is equals to 1, so we get P is equals to AM square by 2. So in this equation, so we have to substitute in place of P, so AM by 2. If you do that, signal to noise ratio becomes 3 into, in place of P, I am writing AM square by 2 whole divided by, so what is G max? G max is the total range. Okay, so from here to So this point, okay. So since G max is, I have assumed this is G max and this is minus G max. So which means that AM is G max minus AM is minus G max. Therefore, since we have Gm square, G max square, we will get AM square. Amplitude of the message signal is AM, okay. So AM square will get into 2 to the power 2v, I will write it as it is. So if I simplify this, so you have AM square here, AM square here, it get cancels. So you will come up with 3 by 2, correct. So it is 3 by 2 into 2 to the power 2v. 3 by 2 is, we know, it is 1.5 into 2 to the power 2v. This is the signal to noise ratio, okay, for a linear quantizer assuming sinusoidal signal, message signal, okay. Let us represent this in decibels. We know that whenever you want to convert or represent in decibels, we take 10 log of the answer. So if I take 10 log of the previous equation, that is 1.5 into 2 to the power 2v, so it becomes so log of a into b, log a plus log b. So it is 10 log of 1.5, 10 log of 2 to the power 2v. So 10 log of 1.5 is 1.76, okay. So plus, so you will get so 2v will come here, okay. So 2v into 10 it becomes, so 2v into 10, so 2 to the power 2v, a to the power m is m into log of a, correct. So therefore 2v will come here into 10, I will write it as it is. Log 2 is 0.3. So if you simplify that again, so you will get it as 1.8 plus 6v, 1.8 plus 6v. If you multiply all these terms, so you will get it as 6v. 1.76, I have rounded it off to 1.8, okay. So this is signal to noise ratio of a uniform quantizer assuming sinusoidal signal, and we got 1.8 plus 6v. Thank you everyone.